So welcome. Thank you all for joining this webinar about the Raspberry Pi Pico board and the RP2040 microcontroller. So my name is Clemens Valens. I'm a technical manager at Elektor Labs, and I will be moderating this webinar. Here we have a summary of what we will be talking about. As you may know, last January, the Raspberry Pi Foundation took the world by surprise when they suddenly launched their own microcontroller, the RP2040, and the development board to go with it, the Raspberry Pi Pico. Here you go. So why did they do that? And why this microcontroller? Here it is. We will try to answer these questions in this webinar, as we have with us today Sir Raspberry Pi, Eben Upton. We also have SparkFun, the American manufacturer SparkFun, who launched already three RP2040 boards. And with us also is Nathan Seidle, who is the founder of SparkFun, and he will tell us a bit more about these boards. At the end of the webinar, we will give away a few of these boards and also a book, but to the people who will still be there at the time. Note that during the webinar, you can type in questions in the chat box in the right corner of your screen. I hope I'm pointing to the right now. We will try to answer them at the end of the webinar. Okay, so let me introduce now the guests that are with me today in no particular order. So we have Eben Upton. Thank you for being with us here today. Eben is co-founder of the Raspberry Pi Foundation and CEO of Raspberry Pi Trading. He will enlighten us on the motivations behind the Raspberry Pi RP2040 microcontroller, or at least that's what we hope. My second guest is Nathan Seidle, founder of SparkFun. He is located in Boulder, Colorado, which is not far from the center of the USA. Hi, Nathan. Nice to meet you.
Thank you.
Nathan will tell us more about the SparkFun products based on the RP2040. I've also been told that SparkFun will be giving away a few of these boards to our viewers. I hope you are aware of this.
Yeah. Yes, indeed.
Good. Last but not least, we have Matthias Clausen, our engineering editor from Elektor, all the way from Aachen, Germany. Hi, Matthias. Thank you also for joining us here online. So before we get started, please let me remind you once again that we will be giving away 10 Raspberry Pi Pico boards, also a bunch of these SparkFun boards. I don't know exactly which one, and a book that I don't have, which is it's brand new, but an Elektor book about the Raspberry Pi Pico board will be given away also to 10 lucky winners, and that's all. So having said all that, we can continue start our webinar. Note that we published in the April edition of Elektor a short article about the Raspberry Pi Pico board. Somewhere in here. And also note that this edition, by the way, was spell checked by SparkFun. So if you find any typos, contact them, not us. Okay, now over to Matthias, who had a good look at the Raspberry Pi Pico and the RP2040. Please tell us what you think about it, Matthias. The floor is yours.
Yes, thanks, Clemens. We have a slide prepared that shows the board in detail.
Oh, this was the article, by the way, the board here.
Yes, this is the board we are talking about, and also you can see the chip we are talking about. This is a Cortex M microcontroller, a core that can be called industry standard. And in this case, it's a dual core one. And what is uncommon is that Cortex M0 Plus has been chosen. Maybe Eben can give a more detailed insight into that process, why they did that later. The Cortex M0 Plus is the smallest core of the Cortex M microcontroller family. Interestingly, besides having both chips inside, they also add a bunch of nice peripherals inside the chip. This is, for one point, integer division in hardware and also a kind of filter unit for signal processing. This is per core, so you have twice of them. And I think the most interesting thing besides that is the programmable input and output unit inside the chip, which allows you to create peripherals that are not built in hardware, but that can be created in software, and only your creativity is the limitation for that. And something they did, and that is also interesting, and maybe also Eben can give us some words about this, is the use of external flash than rather internal flash. Eben, could you maybe give already a few words why you have done this?
Okay, so this is an interesting. A lot of thought went into the design of this microcontroller, and what we've ended up with is something which I think what we've described as being off leading diagonals. So I think that you have, if you imagine a space with, I guess, processing power and volatile storage and non-volatile storage, you tend to microcontrollers tend to kind of cluster around a kind of a leading diagonal through the space. So you tend to have devices which have a relatively small amount of all of those things. So if you take a Cortex M0 Plus, for example, you might traditionally see that as a lower performance core, and you might couple that with a small amount of memory, a small amount of RAM, and a small amount of flash, or you might say put down a Cortex M4F, which until recently was about the most powerful thing that was available in the Cortex M line. And you would then feel, because you've put down a big processor, you should also put down a lot of RAM and potentially a lot of non-volatile storage. So what we've done with this design is we've picked a relatively modest processor, although we've clocked it very fast. The interesting thing is that the clock rate, because we've manufactured this thing on a modern process node, we've been able to clock it very fast. It's 133 megahertz Cortex M0 Plus. It's actually a lot of performance. But we've had a relatively modest processor. We put a lot of RAM down. Why have we put a lot of RAM down? Because large amounts of RAM make programming easy. Okay, large amounts of RAM, the more mental energy you're putting into squeezing your application into a small amount of storage, the less energy you have available to think about the stuff that actually matters, which is the features of your software and the reliability of your software. So if we put a relatively modest processor, but two of them at a high clock speed, put a large amount of flash, a large amount of RAM, and then we put no flash at all. We pushed the flash off the package. Why have we done that? Two reasons. One, it allows us to go to an advanced process node. Most microcontrollers are built on relatively old process nodes. This microcontroller is built on TSMC's 40 nanometer low power 40LP process. You can get flash for these nodes, but then it's not a node which is particularly well adapted to flash storage. So that's one reason it's allowed us to go to an advanced process node, which brings all sorts of power and performance features. The other reason is that by putting flash off the chip, we've given people flexibility in terms of how much flash they put down with this design. On Raspberry Pi Pico, we've put down 2 megabytes, a reasonable amount of storage. But most of the partner boards, the SparkFun partner boards, have larger amounts of flash. They've chosen to put larger, higher capacity flash packages down there. So it allows us to address a bunch of different segments with one piece of silicon.
Okay, this brings us to another interesting point, the naming scheme you've chosen, Eben. It's called the RP2040, and if you read the datasheet carefully, it indicates that this might not be the last one we have seen from this family.
No. So shall I decode it? Shall I do the decoding?
If you like to.
Yeah, so 2040 is 2040. So let's take the digits in sequence. 2 is 2 cores. 0 is Cortex M0 Plus. 4 is 256K of RAM. So it's 2 to the 4 times 16K blocks of RAM. And then 0 is no flash. So I think you can go and you can invent what a chip which is identical but had 4 Cortex M3s in would be a 4340. It's now inevitably these numbering schemes, they never survive collision with reality. If I can do one more chip and have it fit into this, there's a wonderful example of this back in the 1970s with Intel's naming convention that I think lasted 6 months. But if I can do one more chip that fits into this naming convention, then this will be a successful naming convention as far as I'm concerned.
So we can expect an RP 8.7, for instance? That would be really powerful.
I think an 8.7. Let's put 8 Cortex M7s in a processor. You can certainly invent. There you are. It's a product announcement. That's exclusively. You can invent some really exotic and pointless microcontrollers that fit into this naming system. The question is, are there pointful microcontrollers that don't fit into the naming convention? I think it's pretty much inevitable that there will be.
Yeah. For the naming scheme, as you told, it's Cortex M0 Plus inside. Was there a particular reason not to choose Cortex M3 or M4 for any reason?
Well, so there are a couple of things. Obviously, we've gone for this very advanced process node, which has brought us some energy advantages, some power advantages. One of the big things that attracted us to M0 Plus is it is the lowest energy core that ARM makes. So it's a 2-stage pipeline, and that means for that reason and others, it consumes the smallest amount of energy per instruction executed of anything in ARM's portfolio, and that's obviously very important to us. The other interesting thing about it, the two-stage pipeline turns out to be super useful, right? Because it does mean that your branch penalty is lower. It's interesting when you take straight line, when you take branching code and run it on an M0 Plus, and take the same code and run it on an M0, or any of the other 3-stage pipeline cores, you find that they run slower because you get more of a penalty every time you take a branch. So it is it's a beautiful core, actually. I think ultimately, why did we pick it? Because it's beautiful. We like to make beautiful things, and I think ARM have a number of cores which I would describe as being beautiful, and I think the M0 Plus is one of them.
Okay, thanks for the explanation why you've chosen that, because there were many rumors why not using an M3 or M4. And
yeah, it's interesting. Obviously, I think what's interesting is the power you get out of a high clock speed. This is 133 megahertz. Would I rather have a 48 megahertz M4 or a 133 megahertz M0 Plus? I'd much rather, unless I'm going to do floating point code, I would much rather have 133 megahertz M0 Plus.
Okay.
We have a question on the technology. The person, I have to put on my glasses to read his name, Saverio Minutoli, he asked, if I understand correctly, the technology is TSMC. The silicon cost has increased a lot due to the high demand on consumer market. Will the RP2040 cost more?
I don't expect any cost changes to Raspberry Pi Pico. It's priced at a very sustainable price point for us.
Okay.
While we at this question point, as currently the silicon output of the available manufacturing capacity is limited, have you seen for the Raspberry Pico any shortages or any upcoming ones? Sorry to ask that, but
we are in a shortage situation at the moment. So we're in a backlog situation at the moment. We have taken orders for about 1.1 million Picos, and we've shipped a little over 300,000, somewhere between 300,000 and 400,000 units. So we have a backlog on the order of 800,000, units. We are manufacturing chips at a rate of about between 60 and 80,000 chips a week. So you could imagine, best case, us clearing that backlog in 10 weeks. A couple of things that will stop us from doing that. Obviously, we have a couple of partners of whom SparkFun a very important one, to whom we're supplying silicon. So we are, even though our own product, what's really important to us is that innovation doesn't, and this is a lesson for us really from Raspberry Pi. Innovation doesn't just come from one organization. A bunch of people sitting in one organization, people sit in the room, think real hard, do some innovation, right? The best innovation comes from the community. And so even though we are in a shortage situation for our own product, we are still diverting quite substantial amounts of silicon to partner products. So I suspect we are probably about 3 months away, assuming that no one places any more orders for Pico. And of course, the other lesson from Raspberry Pi is once you get into an in-stock position, people tend to buy a lot more of your stuff. Assuming nobody places any more orders for Pico ever, I would think we're probably about a quarter away from not being what I call shortage.
If I may interrupt a little bit, Eben, that was a really interesting comment and a kind compliment. You said that the best innovation kind of comes from the community. What makes you say that? Was there a specific instance, or is it just sort of a feeling?
Well, it's been what we found all along with Raspberry. I mean, it's what we found all along with Raspberry Pi. Remember, we made a toy for children. That's what we thought we were making. We made a toy for children, and then the people took it to all sorts of exciting places. And so that's the general Raspberry Pi lesson. And what's been interesting, sort of looking at the SparkFun product lineup, is the extent to which these are differentiated from Pico. So Pico is intended to be I think we've said to various people, including you, that we're unlikely to do more than 1 or 2 products of our own with RP2040 in them. But what's interesting is that you found a number of different directions that you can differentiate your products from Pico, and you found ecosystems, the various ecosystems with the kind of the Quick and the Micromod. You found ecosystems that you can plug it into, which multiply the power of the design. And those are really, these are not things that we knew we wanted to work with you guys because we love everything you do. But there wasn't like a plan. I was saying this, there wasn't a plan that if we make this chip here, then SparkFun will be able to make that micromod that they can then plug into a thing that will then do HDMI video output. Literally none of those steps in that chain existed. There's just a sort of a face. They just step off a cliff and someone will figure it out before you hit the ground, right?
Excellent. Thank you.
Yep. We got a few questions coming in. That is one concerning the USB peripheral. Mm-hmm. And the answer to that, the question is the chip also be able to operate as USB host? And it totally is.
And that's very, and I believe Nathan, that's unusual in that I think am I correct in saying it's the only micromod processor board at the moment that does that?
Correct. Yeah. Yep. So the Micromod processor board has a USB switch on it. So if it detects power from USB, it acts in device mode, and then if you battery power it and attach USB, it will go into host mode with the idea that people would hook up flash drives and things. But Eben, have you seen other devices that people have used in host mode? What was the intent of host mode?
Oh, the intent of host mode was to let you build a BBC Micro. Or Apple.
All right.
That was it. I mean, the intent was very simple: plug a keyboard in. That you can't. You see the various sort of bit banged AVR USBs and stuff. It's always been that. If you look back to the start of the Raspberry Pi experience, which was 2006, I had built a thing around AVR. That was a computer, and one of the challenges with those is always, well, what do you plug into it? And the answer often tended to be plug a PSP into it, and that's not super ideal.
Clemens, if you would be that kind to show the actual chip pinout of the RP2040.
By the way, somebody says, I know somebody in the chat says, hopefully no supplies are coming through the Suez Canal. We are early enough we do have supplies of various things for Raspberry Pi that come through the Suez Canal, so we're watching that with great excitement. Keyboards and mice mostly. We are still early enough in this program that everything is air freighted, which has its own challenges at the moment, actually, because air freight relies on, as I'm sure all of us who buy and sell things know, air freight rates typically rely on being able to shove things into the hold of passenger planes, and when there are no passenger planes, there are no passenger plane holds to piggyback on. But yeah, everything we're still in an air freight mode with this, so we're not expecting Pico. The boards are made in Japan and air freighted back and forth.
I never imagined that my freight expense would be related to a COVID vaccine.
Yeah.
And it suddenly is. It's the faster we can get to vaccines, the faster we can all get back on planes, the faster the world logistics can sort of get back to some sort of normalcy.
Yeah, I'm a supply chain guy now, right? I mean, I don't think I did do an engineering degree and in order that I could be a supply chain planner. But actually, you know, it's not the worst diversion in the world, actually. I'm learning new things this year.
Yeah. Stressful, but fun.
Stressful, but fun.
Yep. Also, something to note is the attention that has been put into the pinout of the RP2040. If you look at the pinout diagram from a hardware perspective, personally, I find it really nice that someone really thought how to put I/O pins around the chip. And maybe, Nathan, what was your first idea after you've looked at that one?
I have a lot of very positive things to say about the documentation and the layout of the chip. So I too agree that this was one of the first chips that I looked at the package and said, oh, this is as if someone is going to use their own IC. It was designed as if someone was going to use it. Really appreciated that, and I really appreciated all the work that went into the documentation. It reads very well. I have my own opinions about certain things. That, oh God, what was it? The reset pin is called the go pin, or there's some very fun changes from normal that I really enjoyed.
Run is the run pin. Historical, right? The chips that we, it's the team that did the chip were originally the same people back at Broadcom, actually, who did did 2835, and every chip they did back to when they were a startup before they were acquired had a run pin, and so the run pin makes its way down through the through history, through chip history with that team.
I had some great conversations with Alistair, the person in charge of your documentation. He's a friend of mine that goes back a decade or two. And it's so hard to describe to students why a reset pin is sort of negative, right? And if you rename the pin, it makes it that much easier to teach. And so to think about history and to challenge things, I love it. It drove me a little crazy because I'm an electrical engineer and I see dozens of microcontrollers a year, and you're a little different. But as I absorbed it, it was a pleasant change.
And this is, of course, there's a couple of interesting points there. One's Alistair, of course. This is Alistair Allen, much known to I'm sure many people on this call. Long time sort of technical guy who can also write English, that's an intersection. A bright technical guy who can also write good English is an intersection of two fairly small steps. He joined us a year before launch. At a point where it became apparent we might have it's a state-of-the-art chip, and it would have decidedly non-state-of-the-art documentation. And really, he has not written this entire sheet. What he has done is he's worked with the engineering team to help them document what they've done and to help them put all of that together, because that's come in from 10, 15 different people, and to take all that stuff and put it into a common voice. Which means that it doesn't feel like you're reading, although you are reading 15 different people's work, it doesn't feel like you're reading that. The other one is you point about sort of designing it to use it. You can see when you look at the layout of Pico, this chip has been co-designed with Pico, and that really is it's incredibly rare. It's been designed to, so they're very late in the chip tape-out process. There were pads being swapped around in the pad ring, so that they would then be swapped around in the pin-out, so that you could then reduce the layer count on Pico. What you end up with when you look at a Pico, if you look, if you look underneath a Pico, I'm not sure if we can resolve that really. But if you look under a Pico, you'll see it's almost entirely ground. It's a 2-layer PCB, and the bottom layer of the PCB is almost entirely ground plane. So it's really almost a single-sided PCB with the exception of a tiny number of traces. And that you can only do that if you co-design your. And then that means a number of the other, the Thing Plus, a number of the other sort of stick computer variants then have an easier time than they would have done if we just had a bit of a guess as to what a good ball out would look like.
So, and I may totally mess with the conversation where we want to take it, but Eben, my question to you is how much pushback, what was the chip design process like? My community is doing open source hardware, right? We design PCBs all day long, and there's very, very few of us that have ever designed a chip from the ground up. And so what was it like to go to, is it TMSC, your foundry that you used?
So this is a TSMC, yeah, this is a TSMC chip. I mean, I wasn't deeply involved in the design of this particular IC, but it's a surprisingly tractable. I think the thing about how to describe it, the thing about IC engineering sort of generally is sort of something I've been involved with for sort of 15 years or so. It's one of those things which is either straightforward or impossible, and there are a bunch of roles, and you need to have a really bright person in each of those roles. Okay. If you don't have somebody in all of those roles, then it's basically impossible. You have somebody weak in one of those roles, then it becomes extremely difficult. If you have some of those roles, it's like, I wouldn't describe it as, it's insulting, it's denigrating to the engineers to describe it as trivial, but it's hard in the sense of a lot of bright people working very hard every day, doing the thing they know how to do. I had a house built a couple of years ago. What was wonderful about it, a similar thing, watching really, really skilled people who know how to do one of sort of 15 or 20 different trades, turning up every day and doing the thing that they're great at. And that's the experience of a successful chip project, whether it's a microcontroller like this, or whether it's one of the big SoCs that goes into big Raspberry Pi.
Perhaps, and I don't know if you can speak to this, but to get the pinout, I've pushed back on suppliers before. I've said, hey, I want it this way. And they scratch their head and they say, why would you ever want it like that? And for you as the end user, you know why. So when you were getting the pinout on the IC, TSMC must have had the core laid out, and then to get those, the gold wires, it's bonded to the package. To get that pin out, did you have to cross wires, or did they lay out the core so that everything ran nicely?
That's interesting. So all of the implementation, so you can sort of divide IC engineering into front end, back end. So let's divide it into arbitrarily into front end, back end, and packaging. So front end is RTL work, writing Verilog, and specifying what the chip is going to do. Back end is implementation work, so taking Verilog, synthesizing it into a net list of gates, and then placing those gates on silicon, routing between them, taking the top level, placing the pads on the package in order, placing the pads on the die in order, and of course that's informed and feeds backwards and forward. There's feedback back in both directions between that and the packaging design. And then the interesting extra step here is that then there's another stage of feedback down to the PCB design, which is normally missing from. People will tend to do studies. I mean, I don't think I've ever been involved in a chip where someone hasn't done a rough study of how the chip might be used on the board, but the very detailed feedback is rare. So all of the handoff point from the silicon team to from the design team to the fab is GDS2. So effectively approximately a bunch of bitmaps of what you want all of the layers of the mask sets to look like. All of it was done inside Raspberry Pi. So effectively, delivery to TSMC is a GDS2 file which says go make this, go use your amazing skills to make this thing. And that means that the pad ring design, which couples to the package design, was entirely managed inside Raspberry Pi, as was the package design. And then you then go to an external company to actually have those packages made. There's an interesting sort of fine detail of package design. There's a ground pad in the middle there, so QFN. So it's got a big ground pad underneath. That ground pad is smaller than it generally would be for a 7x7 QFN. What advantage does this give us? It makes the package less moisture sensitive, because what tends to happen is moisture tends to accumulate under that pad, inside under that pad. And then it means there's a baking step during manufacture that we can skip, save some money. It also means that you don't need to keep this in such a controlled environment subsequently to avoid it popcorning when you put it through reflow. So that's what makes it, I think it's an MSL1 pattern.
I thought it was all routing under the chip, but it's also moisture related.
Well, yeah. So if that's a big slug of metal, then there's kind of a long way. Moisture can get a long way in underneath it. If it's a little slug of metal, then that moisture can you can't accumulate so much moisture under it, and so you don't have so much danger during reflow of parts that have been left on the side for a period of time.
Awesome. It helped with routing too.
Yeah. The pad is great. I mean, the pad's actually amazing because it's there's more space around the pad, as you will have noticed, to route around it. But also we've you can see that Pico does this. Actually uses the pad itself then to bridge between. There are two discontinuous bits of ground plane with some tracks cutting. There's a cut in the ground plane, and we actually use that pad to bridge between the two bits of ground plane on the back of the board. It's lovely. It's James Adams. Everything James. I think that it's signed by him. Pi 4. If you desolder one of the USB connectors, you find that it has James's signature underneath it, a JRA. So you can. I would say you can forge checks in his name if you want. This one is actually JRA signed. I think the boot cell button. I think if you desolder the boot cell button off this, I think it just has the letters JRA underneath the boot cell button.
Neat. Yeah. Very cool. Neat little Easter egg. And then again, you can wave me off if you want, but as a community member who's always dreamed of creating their own silicon, can you give us a sense of the cost? What is it? Does it take millions of dollars? Is this totally out of the hands of a beginner or hobbyist of a startup company, or is this somewhat approachable?
I would guess about $3 million for this chip program. That'd be good. It's not one, it's not five. It's sort of three. It's on 40 LP. Which includes the mask set, so the production mask set. Engineer time, tools, IP licensing. Although obviously not a lot of licensed IP in this design. It's so yes, it's within range of, and this is 40 LP. So it's not 5 nanometers. This isn't an Apple M1.
Right.
Right. Neither is it 130 or 180. So I think if you wanted to do a microcontroller on 130 or 180, one of these very, very antique nodes, I mean, you could probably divide that by 3. You probably get I suspect you get $100 million, including your mask set. You probably couldn't. It probably wouldn't be as complicated. There's a lot of subtlety to RP2040 that chewed through engineer time. I don't think that it would be. It's not impossible. It's really not impossible. I think the challenge is getting someone to lend you that money, and not. I mean, it just seems unlikely, doesn't it, to make that a little bunch of people can make a chip. And of course, what we remember is little bunches of people made chips for a long time. There's a story about the original ARM chip. So Steve Ferber and Sophie Wilson went out to see the Western Design Center, where they were designing the 6502 that they'd used for the BBC Micro, and it became apparent to them that it was one guy. But this whole thing, they'd be buying this chip, and it was one guy. And they came back and then sort of seemed to say to each other, well, we're 2 people. We could do that. And of course, they make the ARM, and of course, everything goes from there. So it is possible to do these things in a lightweight way. It's just about having someone who's prepared to pay for it, who's got faith that it's not insane.
Well, I just have to say that you seem to have found the right people for exactly the right position, because everything I've seen, all the folks I've interacted with at Raspberry Pi, incredibly sharp folks. I have to give a shout out to Luke, who's doing all the crazy bit-banged HDMI stuff. It's very smart people.
Amazing you guys who productized that. That's brilliant. That was very, very cool to see that.
I'm glad you didn't mind, because I think it's run a little bit out of spec. You got to run the chip a little bit fast, but it works.
Yeah, you've got to run at 252 megahertz. So which sounds like a lot for 100. So it's, I mean, let's sort of kind of look at this chip. Closed at 133. Very hard to find any silicon that runs at less than 250. There will be slow corner parts that do. It's at 1.1 volts. I've actually never run a TSMC 40LP chip at 1.1 volts before. That's way lower than I've ever gone. So we know this process has got voltage headroom because we use it. It's the same process that we use for Raspberry Pis 1 through 3. We know it's got voltage headroom. So I suspect that what you'll see from us I suspect what you're going to see from us is you're going to probably over the next year see a couple of different operating points. I think you'll see a 1.2 volt operating point, and I suspect that probably is close to bringing 252 within officially supported range. Certainly bring 200 within supported range, I think. The other one you're likely to see from us, I think, is a low voltage retention mode. This is not a nano power design. I don't think anyone builds a sort of ultra low idle power consumption device as their first device, because it is challenging. What we can do with this, though, is we can drop the core voltage. If you're running it, I suspect we can probably drop the core. We need to characterize it. I suspect we can probably drop the core voltage when it's idle, when it's in sleep mode, down to 0.9 volts, and that'll take you down to probably it'll take you down to pretty small number of microamps of consumption, so that's kind of exciting. What's wonderful is once you have a chip, once you have a mask set, once you're making silicon, there's a lot you can do. You can have a lot of fun without blowing another mask set's worth of money.
And is that just batch? Like you're selecting between the batches and you're saying this is the batch that is capable of X?
That's another interesting question. So that's kind of what we've always called speed binning. This is not binned. We don't bin this part at the moment. We could speed bin. That's a third thing we could do along with kind of higher and lower voltage operating points. We could speed bin for speed. We could speed bin for low leakage. So you could make artificially slow parts that leak less. That's perfectly. You can retarget. It's called just retargeting the process. This is just dopants, right? So this is just diffusion. So you can say, I want you to retarget. You have not process nominal, and you say move it up a sigma, move the middle of the distribution up a sigma or down a sigma, and get more speed or get me lower leakage. And we may do all of those things with this. Design.
So tell me, and forgive me, Matthias and Clemens, if you guys want to direct us, however, please. But Eben, why? I mean, to compete in this world of microcontrollers, it seems like more and more have a radio embedded in them. We do a lot with the ESP, and we do a lot with the Apollo, which has a Bluetooth radio built into it. Tell me about the discussion and the decision to forego a radio.
It's really challenging to make radios. It's hard to make radios. I think it's hard to make radios, and there isn't actually a vast world of several things. One, you probably don't do it for your first chip. Even if you do know how to make radios, or you can license a radio from somewhere, you probably don't do it for your first chip. There is actually a paucity of licensable Wi-Fi. I think if you look at, the Apollo has built-in Bluetooth BLE. I think there's a lesson that it's maybe not be what people, BLE may not be really what people want. I think people really like Wi-Fi. And there's a bit of a paucity of licensable Wi-Fi IP out there. So you're kind of constrained to build your own radio. I think Imagination Tech had licensable Wi-Fi, but I think that was sold to Nordic. So it's interesting. Some of the places you could go and license have actually been folded into companies who, obviously Nordic historically, a Bluetooth. So it's quite challenging, actually. But I think we've got to remember that the vast majority of microcontrollers in the world are not connected microcontrollers. They are standalone microcontrollers.
Absolutely.
So we're happy to go play in that space for now. And then maybe later on we can figure out a way at the silicon level or at the board level to do something with radio. And of course, partner innovation. We already have one partner who have a product in development that has a radio on it. So again, the community is kind of delivering for us.
Absolutely, thank you.
Yes, Nathan, it's all very interesting, all the questions you are asking. I think you ask at the same time questions that people ask in the chat box, so it's all very informative. So I let you talk. But this is, of course, eating into your own time to talk about your own board. So maybe you don't have to say anything about them, or you think that everybody will understand why you made this board. This is the, which one is it again? The Thing Plus.
Yeah, I'm a terrible sales guy. I'm a much better technical person. The Thing Plus is
like technical answers, so just to give us technical details.
Fabulous. So the Thing Plus format is also known as the feather footprint from Adafruit. So all we did is we took the feather footprint, we extended it a little bit to add the sort of, we're hoping, ubiquitous quick connector. So you've got the Thing Plus feather footprint that allows you to do many of the shields. What else did we stick on there? We had the micro SD card because we think that more and more data logging applications are going on. That's very, very handy. We internally chose to put a 16 megabyte flash, not 16 megabit, but 16 megabyte. So it's a very, very large piece of flash on there. The reason for that is we think, it's much easier for us to warehouse a single flash size than it is to have 5 different flash sizes. So we have all these different products that needed flash. And so we just decided to sort of go a little big and buy a large quantity and use that across different designs. So works on this board very well. Let's see, the micro SD socket. We also, we put a pixel on there. The WS2812 is an addressable pixel. And that's really handy, we think, for beginners. The first thing you're going to do is blink the status LED, and that's great. But Eben, you've got to tell us about the PIO module at some point, because it's just bonkers. And so I think the next tutorial that folks will really gravitate to is that PIO. And to be able to build your own addressable LED, perfect, thank you. This microcontroller doesn't have hardware built into it to control addressable LEDs, but it has the PIO. And so you can write your own hardware driver for an addressable LED. It really just messed with my head when I started reading the RP2040 datasheet, because Alistair had to explain it to me. I was like, what is this? What are you guys doing? So Eben, would please tell us about the PIO.
So PIO is the Raspberry. So RP2040 it's an attention to detail microcontroller in general. It's just a really, really, really beautifully done microcontroller. The PIO is the sort of differentiating thing. The PIO is the place where we step outside merely implementing a conventional microcontroller really well. And we have a pair of these on the device. Each of them has 4 state machines. So we have 8 PIO state machines. Each block of 4 state machines shares a 32 instruction memory. What's in the instruction memory? It's effectively a set of steps that you go through, that your state machine will go through, a set of states the state machine will go through in order to interact with the outside world and interact with the system. So you effectively have FIFOs that take data from the system bus matrix into the PIO. You have FIFOs that take data from the PIO back into the system bus matrix. And inside the PIO, you're basically consuming those bits, bits from the input FIFO, and then deciding how you're going to put those onto physical pins in the real world, or you're observing physical pins in the real world and figuring out how to pack that data up, how to sample that data, pack that data up and put it into the FIFO. Really, the motivation here was to be able to implement as many different peripherals as you can, as you said, without putting hard peripherals on. We didn't really have the courage of our convictions, as you can see from the diagram. We did put a couple of I2Cs, a couple of SPIs, and a couple of UARTs on there. And yeah, they are fine hardware peripherals. I think particularly the I2C, actually, it is a little bit hard to do a really good I2C slave if you don't have a dedicated piece of hardware. But it's a... but yeah, for example, you mentioned your SD. You mentioned your SD card there. Of course, we don't have an SD card peripheral on here, but there's an SD card, a very capable SD card peripheral implemented in PIO. Although you did reverse the bits, I hear from Graham. Graham Sanderson is one of my very, very oldest friends who lives in Austin and works on this stuff. I think I can hear the swearing from 6 time zones away. But it's good. But it's a great demonstration of the fact that the PIO will soak up. Obviously, what did that buy you? I guess it bought you. Bought you. I think it's
bought me.
What did it buy you? I have a 3-year-old daughter, and so some of my grammar has become a little bit damaged. The ability to have simpler PCB tracking, I'm guessing, because yours is on the back of the board. I think all the SD cards we've met before have been on the front of the board. What he was able to do was he was able to soak up that hardware, so you can save. It's all about system cost optimization. You're able to save system cost by soaking that up into the PIO. It's lovely, and the range of stuff people have done with it. I've seen people doing Ethernet with it. I've seen people doing HDMI with it. Who saw that coming? SD card, DPI, I2C, SPI, and UART, so soft versions of the hard. Of the hard peripherals. And of course, one thing, if you're using it to do, even if you've got a suitable hard peripheral on the board, maybe it's not on the right pins. We try to be flexible with the muxing options. What PIO will let you do is it has complete flexibility in terms of how you map its pins onto physical.
And I have to admit, that's one, it makes hardware layout folks a little bit lazy. So what happened with the SD socket was we were told that the PIO could handle anything. We said, okay, great. We'll just do it in software. And so we wired these pins. We wired them. I didn't think it was an issue. We wired them in reverse order. We were told they had to be consecutive, but we were not told they had to be increasing. And so we wired them up. And then, your engineer in Austin, Texas, he groaned and he worked with us and was able to implement at a bit of a transfer cost. It doesn't run as fast as the consecutive increasing PIOs. But it makes us lazy. It means we don't think about as much what pin has to be connected where. We just sort of say, hook it up, and we can do it in the PIO.
And microcontrollers are, most of my microcontroller experience is actually AVR8. And the thing with microcontrollers is that they're bits of glue, right? They're bits of glue that stick things together, and they're bits of glue which bring hardware problems into the software domain. And if there was a dream for this chip, if there's a vision for the chip, it was to extend that. So why are there two cores? Well, there are two cores so that one core can manage hardware, while one is the application core. So either one core can supervise PIO, or if you find something that PIO can't do, one core can actually just sit there, and it has the GPIOs right there on the SIO. You can just sit there and bit bang, 133 megahertz, just sit there and bit bang pins all day long. And you still have a dedicated uninterruptible, you can have that be uninterruptible. A lot of the bus matrix is designed to allow you to not have contention between that high priority core and the application core, and then you can have your other core just run MicroPython. So that's a whole thing about trying to push hardware problems into software, just because they're more tractable. And the iteration times are so much quicker in software. The iteration time for a professional piece of hardware like this is at least days, even if you've got access to a short-term PCB shop. It's at least days. The iteration time for software is seconds.
Yes, this brings me to a question we have in the chat box. Eben, can you comment on the potential of the RP2040 for industrial applications?
I hope it finds some industrial applications. It's designed to an industrial, like all Raspberry Pi products now. It's designed to an industrial spec. We probably will do some qualification work at some point around package. We aren't qualified to. I think we're qualified to an industrial, but not to an automotive temperature regime. And so we'll probably do some work there to broaden that regime out a little bit. Once we're still bedding into it, first chip. But we'll do some stuff there. I'm sure it'll find industrial applications. Particularly think it'll find industrial applications once it's in ready general. Once the chip is in general supply in a quarter or so's time. I suspect this year the general tightness of the semiconductor supply chain will mean that it will probably quite quickly find industrial applications because it's available.
Okay, I think because our time is we have about 12 minutes left officially. I think maybe we should move on to the Q&A session now, unless someone has to say something really important.
Well, I would just say the micro mod thing is the one, but I'm personally most excited about, because that's such a rich ecosystem. I think this is really the one that's gonna unlock the kind of the distributed innovation. is gonna come from this one, just because just because of the breadth of the ecosystem and the breadth of the accessories that you can
I
already
appreciate
buy.
that. Thank you. That was the intent, was to sort of, as a user with the Micromod situation, you start with whatever microcontroller you want, and then as your project or your development changes, you have the ability to switch. So yeah, I suspect folks will have. I hope folks will have Micromod stuff where they use the STM or the Artemis or any of our processor boards based on the NRF, and then they go, oh, cool, let's go play with the RP2040, and all they got to do is switch out that processor board and begin to poke at it and see where it benefits them. So yeah, it fit really nicely. I think we were able to wire every single pin on the Micromod processor with just a couple duplicates. So yeah, nicely done. It's got a lot of GPIO.
It'll be fun.
Okay, let me check the questions in the chat box. There's a question, when do you expect the first RP2040 to be on Mars?
Oh, I have previously mailed the obvious gentleman to see if he would be interested in flying a big Raspberry Pi to Mars. He didn't get back to me. So if you're watching, Alan, then it's very happy to talk. I don't think we've actually got outside low Earth orbit yet with any Raspberry Pi product. We have at any given time we have two Raspberry Pis on the ISS for the Raspberry Pi educational program. What's been fun for us is to realize actually at any given time there are way more Raspberry Pis than that on the ISS, because they are used to run a lot of experiments. When people send temporary experimental payloads up, they use Raspberry Pis. I'm sure RP2040 will make its way onto the ISS pretty quickly. I would still really want to get out, like everyone, I want to get out of low Earth orbit. 50 years boring a hole in the sky, right? So I'm hopeful that we might make it at least to the moon, if not to Mars, fairly soon.
A question here. I don't know what sea lion is, so that must be my...
It says development environment. Graham uses it, actually. So I suspect sea lion, of all the possibilities, I suspect sea lion's probably likely is towards the top of the list because Graham likes it. A lot of what we do here at Raspberry Pi is driven by what the engineers like, and Graham likes it.
Yeah.
And then we get this question about Python and Arduino. I saw on Twitter this week that someone developed an Arduino plugin or sort of a boards package for the RP2040. I also know that Arduino announced an RP2040 board, but it's still only announced. I don't know why they are late. Are you working closely together with Arduino?
Yes.
Is Arduino important for you?
It's very important to us. They're on the early access. They are one of only 4 companies on the early access silicon program. So they are important to us. We're great friends with them. We've learned a lot. We've learned a lot from them and enjoyed hanging out, particularly with Massimo over the years. Do I think I'm quite a believer for beginners in high-level languages. I think that it's a big change that's coming. Of course, you can see that people do a lot of this on the Arduino platform now that there are Arduinos with ARM Cortex processors. People do a lot of high-level language stuff. So it was certainly one of several reasons why we haven't and won't do a port of our own port of the Arduino C environment to the platform. There's a number of good reasons for not doing that. But one of them is probably for our beginner audience, for our hardcore audience, for the sort of professional design engineer audience. We wanted to build a C library, which was a C SDK, which was very targeted to our platform, which is very lean and targeted to our platform. And then for the more beginner audience, we wanted to focus on high-level languages. But that's just our decision making. And I think once the Arduino product is in the market, I think we will see a lot of people who I would consider to be beginner hobbyist people doing C programming, which is great actually, because it gives them a ladder into the world of C. If I want to program microcontroller, I'm going to program it in C. So it's nice to give people that ladder.
Okay. Here, can we, will the RP2040 appear on mainstream Raspberry Pi boards, maybe on the Raspberry Pi 5?
There isn't any money.
Oh.
There's no money in the bill of materials for it. A Raspberry Pi doesn't have an ADC on it. Raspberry Pi is a single board computer, doesn't have an ADC on it. Why doesn't it have an ADC on it? Because not everybody wants an ADC. So if you want an ADC on a Raspberry Pi, put it on a hat. So there isn't a bill of materials space for a 10-cent ADC in the core Raspberry Pi platform. So there wouldn't be room for an RP2040 in there. Will some of the technology make its way into future big? I mean, we're a long way away from thinking about Raspberry Pi 5 at the moment, but will the capabilities and some of the technology make their way into Raspberry Pi, future Raspberry Pi products? Yes, almost certainly. I mean, PIO is a gem. And I'd specifically love to see PIO in a big Raspberry Pi, but like I say, we're a long way away from that at the moment.
I would like to go back to the slide mode, but I don't know how to do that. Yeah, thank you. Because we're nearing the end of our webinar, and we still have the giveaway to do. So I don't know who wants to go first. We have, I think, Beatrice in the background who will draw some names for the list. There are some 200 people still there. So can you give us 10 people for, let's say, the Pico board? Let's see if something pops up in the chat.
It did briefly, yeah.
I don't see anything. Here, message. Scroll away. Yeah, here we have for the Pico boards. I don't know if I can publish it. I will read them out loud then. So the Raspberry Pi Pico boards will go to Jan Larsen, Jesse Robinson, Tim Stocker, Anderson Neves Cruz, Chris Kent, Henning Kruna, Daniel Uitenhoven, Wayne Mitchie, Igor Ferencic, if I pronounce it correctly, and Ronald Smeets. Then we have the SparkFun boards. Nathan, can you say exactly what we are giving away? Because it was not clear to me. It seems to be a combi.
I believe it's 10 of each. So it's 10 of the Pro Micro, 10 of the Micromod, and 10 of the Think Plus.
So each person that I will name now will get 3 boards. Is that it?
Works for me.
I'm going to have to bid up my offer now. I'm not sure anything else. I do give everyone a Raspberry Pi Zero as well.
Okay. Well, I have here for the why there are SparkFun boards. I have Ivo Simicevic. I hope you recognize your name. Martin Diaz, Arsène Levrault, Daniel Sanchez, Severio Minutoli, Luis Martinez, Sule Johansson, Hervé Tavernier, Roland Muller, and John Decker. And then I have a second list of Pico.
Yeah, who's getting books and who's getting boards? Which list is the books and which is the board?
The first one was the board, and this is the this is also a board. There's also books. The books. Which one is the books? Well, let's say the first one were the boards. So the list: Jan Larsen, Jesse Robinson, Tim Stocker were the boards, and we now go to the book. That is, I think, Jesus Cardona, Peter van Dalen, Corné Vogt, Joseph Havlicek, Johan Maas, Nigel Brown, Bukasa Tsilombo, Alexander Skoglund, Arie de Munk, and Marvin Colon. So all these people, congratulations. Yeah. We will contact you because we will need your address, of course, to send all these things to. Unless one of you 3 have something important to say, then I can think we can say thank you for watching and participating in this webinar. And I hope you learned something from it. I did. I found it very interesting. Thank you, Eben. Thank you, Nathan. And thank you, Matthias. And hope you join us next week, next Tuesday, when we will have a webinar about the Max 78000 AI Neural Network Accelerator, which is, of course, very interesting and which is part of a contest. So there again, you can win some stuff, but real cash and not just silly microcontroller boards like these. Okay, well, thank you for watching. That's it. Have a good day. See you next time. Goodbye.
Bye.
Appreciate it. Thanks for watching, everybody. Cheers. Bye-bye.